Today, I'm excited to share a unique project, banana leaf disease detection. Introducing a smarter way to protect banana crops. Banana cultivation is crucial for food security and income in tropical regions. But leaf diseases can silently spread, reducing yield and hurting farmers. Manual inspection is slow and error-prone. Often it is too late before the damage is noticed. Our project combines vision transformers with convolutional neural networks to detect diseases early with speed, accuracy, and intelligence, empowering farmers with AI-driven tools to secure crops, increase yield, and ensure a healthier future. Entire development process. Step 1. Image preprocessing. Transforming image for model input. Step 2. Feature extraction. Extracting important visual features. Step 3. Model training. Using extracted features to train the model. Step 4. Disease classification. Predicting disease class using learned features. Before we start with the code, head over to Google and search for Banana Leaf Diseases Detection AI Online Course. On the AI Online Course, you'll find the complete guide with detailed explanations and well-structured content. Mount Google Drive to access its files in Collab. Install necessary library. Installs TensorFlow and Keras libraries. Imports libraries for building, training, evaluating, and visualizing deep learning image models using TensorFlow, Keras, Sklearn, and Plotly. Image dataset loading and splitting. Loads and splits the dataset with rescaling from Google Drive. Creates a training and validation data generator that loads and resizes images to 224224 with categorical labels and batch size of 32. The dataset was successfully loaded with 1,280 training images and 320 validation images, evenly split across 4 classes. Calculating and displaying class weights. We calculate balanced class weights to address class imbalance during training, print the mapping of class indices to class names, display the weights assigned to each class, and show the class names of a sample batch from the training data. All 4 classes have equal weights, showing balanced data. Sample batch contains mixed class labels. Visualizing training images with class labels. Fetches a batch of 32 training images and labels, then displays them in a 4x8 grid with class names as titles using Matplotlib and Seaborn. We apply the Sobel Edge detection filter to a batch of RGB images by converting each to grayscale, computing horizontal and vertical gradients, combining them to get edge intensity, and returning the processed images as an array. Visualizing Sobel Edge detected images. This code plots a grid of Sobel processed grayscale images from the training batch, displaying 32 images with their corresponding class names as titles for easy visual interpretation of edge features. Train Generator is a directory iterator that loads image batches from a folder. Building a CNN model. Accepts 128 RGB color images with 3 channels. 2 SONV 2D layers with 64 filters extract low-level features like edges, followed by batch normalization for stable training, max pooling 2D for downsampling, and dropout 0.3 to reduce overfitting. This block, similar to the first, but uses 128 filters to capture more complex patterns, with a higher dropout rate of 0.4 to reduce overfitting due to increased model complexity. Increases filters to 256, capturing more detailed spatial hierarchies. Deepest block with 512 filters, capturing high-level features, using 0.5 dropout to prevent overfitting. Global pooling and dropout reduce features. Dense layers with dropout learn patterns. Final softmax layer predicts 4 classes. CNN model compilation and summary. Now, compiles the CNN with Atom Optimizer, categorical cross-entropy loss, and metrics for accuracy, precision, recall, and AUC, then prints the model summary. Model training trains the CNN model for 10 epochs using the training data, validates on the validation set, and applies class weights to handle class imbalance. Training accuracy improves to 73%, but validation accuracy stays at 25%, indicating overfitting and poor generalization. Vision Transformer Model Implementation. This custom transformer block combines multi-head self-attention, a feed-forward neural network, layer normalization, and dropout for regularization, forming a core building block for transformer-based models in TensorFlow. Defines the forward pass with attention, feed-forward layers, residual connections, and normalization. This multi-head attention class initializes a custom attention layer by splitting the input into multiple heads. It includes dense layers to compute queries, keys, and values, and a final dense layer to combine the outputs from all heads. The embedding dimension is evenly divided across the specified number of heads, computes scaled.product attention, and returns the output and weights. Separates input into multiple attention heads by reshaping and transposing the tensor. Processes inputs through multi-head self-attention, and combines the results into the final output. The Vision Transformer class builds a model that splits images into patches, embeds them with positional and classification tokens, processes them through multiple transformer blocks, and uses an MLP head for classification into the target classes. Extracts and flattens image patches into patch embeddings, processes input patches with positional and class tokens through transformer layers, then classifies using the MLP head. We initialize the Vision Transformer model with a 224 input image size, 16 patches, 12 transformer layers, 128 embedding dimensions, 8 attention heads, 256 MLP units, 4 output classes, and 0.1 dropout for regularization. Then compiles the Vision Transformer using the Atom Optimizer and categorical cross-entropy loss. It tracks accuracy, precision, recall, and AUC as evaluation metrics. Train the model. We train the Vision Transformer for 40 epochs with training and validation data, using class weights for imbalance handling and a learning rate scheduler that decays the learning rate after epoch 10. Although early stopping is defined, it isn't applied in the training callbacks. The Vision Transformer showed low accuracy 25 to 27% and AUC 0.50, with near zero precision, and recall on validation data. Despite learning rate decay and class weighting, the model failed to generalize, indicating underfitting or data issues. Now, Plot Performance generates a 3x2 interactive subplot using Plotly, visualizing training versus validation trends for accuracy, precision, recall, AUC, and loss from a Keras history object. It helps in diagnosing underfitting or overfitting during model training. Model Evaluation Summary. The Evaluate Model function takes a trained model and a data generator, predicts class labels on the data, computes the confusion matrix, and classification report. This command plots training and validation metrics accuracy, precision, recall, AUC, and loss for the custom CNN model using the history CNN training history. The model overfits, showing better training than validation performance with unstable validation loss. The Vision Transformer shows modest training improvements, but struggles to improve validation metrics, indicating limited generalization and possible underfitting. Output shows unstable, stagnant metrics and poor learning, likely due to bad tuning, unsuitable design, or weak data. Now, evaluate the CNN on validation data by predicting classes, showing a confusion matrix, and printing a classification report with key metrics. The model mostly predicts only the healthy class, failing to detect others, resulting in low overall accuracy 25% and poor performance on disease classes. Now, save the trained model CNN in HDF5 format as modelcnn.h5, allowing you to load and reuse the model later without retraining. The evaluate model function assesses the vision transformer's performance on validation data by generating predictions, computing and visualizing the confusion matrix, and printing a classification report with precision, recall, F1 score, and support for each class. The vision transformer shows weak class-wise predictions, especially low recall, indicating difficulty in correctly identifying most classes. The vision transformer model is saved in the .keras format, preserving its architecture and waits for easy loading and reuse later without retraining. Ensemble disease prediction and display loads the image, displays it without axes, and sets the title to show the predicted class label. The predict with voting function predicts the disease class by averaging the prediction probabilities from a CNN and a vision transformer after preprocessing the input image for each model. It returns the final disease label using the class mapping. Display image with prediction shows the image with the predicted class as the title and hides the axes. Banana leaf disease prediction display. You're loading an image from the path, predicting its class using combined CNN and VIT model voting, then displaying the image with the predicted class as the title. We successfully built the banana leaf disease detection system using vision transformer and CNN models. This AI-powered solution enables early and accurate detection of leaf diseases, helping farmers take timely action and protect their crops. Stay tuned for more exciting AI projects. And don't forget to visit Aionlinecourse.com for more AI project tutorials and resources. That's all for today's video. Thank you for watching. If you liked this project, don't forget to hit the like button and subscribe for more tech tutorials.